Today's lecture will focus on ant colony optimization. So ant colony optimization falls into evolutionary computation. We've looked at evolutionary algorithms previously, and in today's lecture we're going to look at ant colony optimization, and in tomorrow's lecture particle swarm optimization, which is also an evolutionary computation technique. So if we look at evolutionary computation, it's comprised of a number of different techniques. These techniques essentially take analogies from how things work in biology. So as you saw with evolutionary algorithms, these algorithms are based on Darwin's theory of evolution. We start off with a randomly created population, then we improve that with the idea of the fittest, survival of the fittest. We use fitness to drive the search in the search space to lead to a global optimum to find a solution to a problem. In this course, the two other types of evolutionary computation technique that we're going to look at is ant colony optimization, which we're going to look at in today's lecture, and particle swarm optimization, which we're going to look at in tomorrow's lecture. So like evolutionary algorithms, ant colony optimization is a meta-heuristic. And as its name suggests, it basically mimics the behavior of how ants work. So how ants survive on a daily basis, how they gather food, how they make sure that they don't waste time taking paths that are longer. All these initiatives of ants that they use for survival in their daily existence is what is used to now solve optimization problems. So like evolutionary algorithms, ACO is also a population-based method. So remember, with population-based methods, we have more than one element of the population, and each element represents a different point in the search space. So here, the ants represent your ant colony is your population, and each ant finds a different solution. When we have a population-based method, we also say this is a multi-point search, because what's basically happening is that each point in your population is representing a particular point in the search space, and therefore it's a multi-point search. As I just mentioned, basically your colony of ants is a population, and your ants then try and find different solutions that can be used to solve the problem. Some solutions will be of better quality than other solutions. So ACO has been good at solving combinatorial optimization problems, but specifically discrete combinatorial optimization problems. You also get continuous optimization problems. So a typical discrete optimization problem is something like the traveling salesman problem, which you looked at for assignment 1. And this problem essentially involves a traveling salesman that needs to get from one city to another. The idea is he has to visit a set of cities, and no city must be revisited, and he must start and he must stop at the same city. And the tour that starts at one city and ends at the same city without revisiting a city must have the minimum cost. So that's essentially the traveling salesman problem. Like I mentioned, ACO is good for discrete optimization. So any problem variables involved must be discrete variables, not continuous variables. Where does this whole idea come from? So if we look at what ants do, how do they function on a day-to-day basis? So the whole idea is the ants live in a nest. They travel from the nest to actually get food sources, and they get to go back to the nest, and that's their basic existence. So the whole process of going to get food and come back is actually planned quite well. And it's very interestingly that intuitively they can try, or they will try and find the smallest or the lowest distance path to get from the nest to the food and back to the nest again. So the aim is to minimize the distance traveled, but they do this instinctively. So you'll notice that if there's a path that's shorter, they get to the nest and back quicker. So the next set of ants will then use a shorter path rather than a longer path. And this is all linked to the whole idea of pheromone. So when ants actually travel and they find food sources, when traveling to food sources, they deposit pheromone. The other ants coming after them smell a path with this pheromone, and they actually follow the paths with their pheromone to also go and actually pick up food from food sources. So you can see this is basically a teamwork initiative, and it won't work otherwise. One set of ants, whatever they find, they share it indirectly by pheromone deposits. So now you end up with pheromone trails. So a pheromone trail is basically a path from the nest to the food, and a path back. And trails that have strong pheromone are trails that are followed by other ants. So how do the pheromone trails get there, or pheromone paths get their strength? So usually if you find that one set of ants initiated a path and it led to food, and there was maybe a shorter path, based on the pheromone, a second set of ants will also follow the same path, and possibly a third. So the more ants that actually follow the path, the more pheromone deposits there'll be, and the stronger that path will actually be in terms of pheromone deposits. And this will continue to attract other ants to actually travel using that path. Over time, some paths may no longer be that good. The ants may find newer paths that are shorter. And what will essentially happen in nature is, over time, that pheromone is going to evaporate on that path. And then we try to find the same analogy when we're implementing it using ant colony optimization. So the artificial ants are dependent on the real world ants. We spoke about ants collecting food. So these artificial ants mimic the real world ants, and the equivalent of collecting food is actually finding a solution. So your artificial ants try to find a solution to a problem. So when it came to finding food, ants would have to decide which part of the trail to follow, which direction to move in each time, whenever there was a branch in a trail. The equivalent in finding a solution is to decide which solution components to add to a partial solution. In artificial ants, we also have to mimic the whole idea of pheromone deposits. So we have the idea of pheromone deposits. You get the pheromone updated after ants find solutions, and the pheromone is updated based on the quality of the solutions. Depending on whether you have a good solution, you want to increase the pheromone value, and of course, if you have a poorer solution, you want to decrease the pheromone value. But in order to emulate the whole idea of pheromone evaporation, what happens is that we get a pheromone evaporation rate, because we want to mimic what happens in nature where things naturally evaporate. So whenever the pheromones are updated, firstly, there's some decrease in the amount of pheromone to represent evaporation. And then those solutions, or those trails that have a better quality solution, their pheromone deposits are then increased. So how does this happen? So remember when we looked at evolutionary algorithms, these algorithms worked in a solution space. Here the ants traverse a construction graph. So basically your nodes will represent something, and your edges will represent something, and that depends on the problem domain. But essentially collectively they represent solution components. So your ants that are traversing this graph will either decide which node to follow or which edge to follow. Each edge of the graph has two values, and the one value is the pheromone value, and the second value is a heuristic value. Now that heuristic value is problem dependent. Both these values are actually used when constructing solutions. When the ants construct solutions, they use a probability rule to decide which solution component to select, and both these values are actually used in that solution component. So for example, if you were applying ACO to the traveling salesman problem, the graph will have nodes, and each of those nodes or vertices will correspond to a city. So remember, the traveling salesman problem is the problem of a salesman that has to visit n cities. He has to start at the same city and end at the same city, and no city can be revisited. And one of the aims of the problem is to actually find a route that starts at the same city, ends at the same city, doesn't revisit a state, but has the minimum cost associated with it. So you can think of it as the minimum distance traveled. So if we look at that example, each node in the graph will basically represent a city, and the arcs will represent some proportional distance between those cities. And that is one example of how you can actually apply ACO, and that's to the TSP. The problem is actually suitable for applying ACO. It maps nicely to nodes in the graph. So if we look at the ACM algorithm, it starts off by setting parameters and initializing pheromone values. So when we speak about parameters, what are we speaking about? So firstly, one thing that has to be decided on is the number of ants. So remember, as I said, the solution space this time is represented as a graph, and essentially a directed graph. It has nodes, it's connected with arcs, and different ants will actually traverse this graph to find solutions. So the number of ants is something that's initialized. Whenever the ants construct solutions and whenever the pheromone values are updated, then there are rules to do this. And different ACO algorithms have different rules. And those rules sometimes have parameters. So those rules will have different values that need to be initialized. The other set of values that need to be initialized is the pheromone values for each ant and for each trail. Usually these are initialized to 1, which seems to work quite well. So as you can see, the algorithm is made up of 3 steps, and those 3 steps are performed until some termination criterion is met. So what is the termination criterion in this context? Examples of a termination criterion used are things like the maximum number of iterations, the amount of CPU time. So the best one to use is basically problem dependent. The first step in applying ACO is each ant will be randomly associated with the vertex, so in the graph, and then from that vertex it then creates partial solutions. So at each point it has to make a decision of which direction to move in to get to the next node in the graph, and that's where a probability is used. So if we look at the equation, the Cij stands for a component, a solution component, and that's for s to the power p. The s to the power p basically represents the partial solution that's being created by the ant. So each time as the ant traverses the graph and moves from one vertex to the next, it's building up on this partial solution, which is essentially at the beginning an empty set, and then it adds components on. So this function or probability function is used to decide which component to add on next. So if you look at the numerator of it, there are 2 values. The tau rij actually represents your Ferromni update value or your Ferromni value, and the second value actually represents your heuristic value. Alpha and beta are parameters, so it depends. You can actually set them. They work. Different values work well for different problem domains, and then that's taken by the sum of all the possible solutions that have been found, all the Ferromni values times the heuristic value. So your n(s to the power p) is basically the neighborhood from the node that you're at. It's all the possible solution components that can be reached from the current node or the current solution component. So this process will continue of the ants then working from one point to the next. For the traveling salesman problem, for example, it would have to traverse the entire graph because that represents all the cities. Each node represents a city, and it collectively covers all the cities. So basically, the ants move through the graph, creating more than one solution, each ant a different solution. So once all the solutions have been constructed, then the next step is to perform local search. So you've got constructed solutions, and local search is applied to this. Now, local search, this step of performing local search is actually an optional step. local search is one of the things that can be performed here. So essentially what's performed at this point are things that are not carried out by individual ants, but basically things that can be applied to solutions as a whole. So that's the aim of the step. This is a step in a number of the algorithms you'll see in the literature. When you see an ACO, a multi-heuristic algorithm, you'll see these are also called daemon actions. So local search is just one of the possible daemon actions that can be performed. You can actually perform other actions as well. So the last step in this loop or this iterative process is to update the ferromni on each edge, or the ferromni for the path as a whole. So the rule that's used to update the ferromni values and the rule that's used to decide which solution component to choose, these differ from one ACO algorithm to the next. So one of the rules that's commonly used to update the ferromni value is this rule. So basically, the new ferromni value is 1 minus rho. Rho in this case represents the evaporation rate, and it falls in the range of inclusive 0 to 1. And that's multiplied by the current ferromni value. And then basically that's summed with rho times the fitness values of all the across the different components in your solution component. So that's what the f of s is. It's the sum of the fitness values of your solutions that have been found. So that together makes the update rule, and there's just one update route that has been used. There are other update routes. Some update routes are based on looking at the best fitness value. Often the fitness value is just the objective value. So if you're looking at the traveling salesman problem, the fitness value will be the objective value, which is the cost of the path that's been traveled. So like I mentioned, there are variations of ACO algorithms, and the variations basically differ in terms of the update rule for your ferromni values, but also in terms of the probabilistic rule that's used to actually choose which solution component to add on next. So there are different variations. The classic system is the AND system. Another very effective system is maximum colony, and then also another popular ACO algorithm is AND colony system. So this basically brings us to the end of the section on AND colony optimization. In tomorrow's lecture, we'll look at particle swarm optimization. In the TUT on Thursday, you'll look at an example, or you'll be given an example where you'd have to apply ACO and define how it will be represented to apply ACO to it.